The goal of this video is to prove this three-part statement about open sets in a metric space. We will prove each part. The first is that the entire metric space and the empty set are always open. So every possible metric space has at least two open sets, the entire space and the empty set. The second is that, if you read through this, it sounds very technical. So if A sub lambda is open for each index little lambda in some large indexing set, capital lambda, then the union of all of the A sub lambda, that union is open. Okay, I said that sort of strangely because I was trying to translate the symbolic phrasing into spoken words. But what it really says is any kind of union of open sets is open. My usage here of this index lambda is trying to say that I don't know what the union looks like. It could be a finite collection of open sets. It could be a countably infinite collection of open sets, or it could be uncountable. But the conclusion of the second statement is any kind of union of open sets is open. Whether it's finite, countably infinite, uncountably infinite, doesn't matter. The third one, on the other hand, is different. So contrast this one with the second line. This says if we have a finite collection of open sets, here denoted A1 through A subscript capital N, where that's our cutoff point, we have a finite collection of open sets, their intersection is open. So the entire space in the empty set, always open. Any kind of union of open sets is open. Say that to yourself like 10 times. Any finite intersection of open sets is open. Okay, we will prove each one, as I said a moment ago. The first proof is going to be super short, and then we will compare and contrast 2 and 3 as we complete them. There's not much to show for this first piece. Consider any metric space. Let X be an element of the metric space. The epsilon neighborhood of radius 1 is also in the metric space. So the ball around X of radius 1, like the open unit ball, if you will, around this element, is a subset of the metric space because it's not going to contain anything else. The metric space is where we are working. Since any element in the metric space has an epsilon neighborhood which stays in the metric space is open. We will just do the empty set out loud. The statement I want to show for a set A to confirm that A is open is if X is in A, then there's an epsilon neighborhood around X contained within A. The hypothesis is false for the empty set. There is no element in A. So it's vacuously true. Okay, so that's just out loud. Since there is nothing in the empty set, the definition is vacuously satisfied. All right, so the entire space in the empty set, always open. Let's look at the next one. The second component of our statement is any kind of union of open sets is open. Again, this notation here is avoiding using something like I in the set of natural numbers or something like that, because I don't need this to be an indexed countable set. We could have an open set for every complex number or something like that. So just doesn't even matter what the collection of open sets looks like. A union of open sets is always open. Okay, so for the proof, we are going to do what I said a moment ago when we were addressing the empty set, which is if X is in the union, then X has an epsilon neighborhood around it contained in the union. That's what we want to show. Suppose X is in this union. What is the requirement to belong to a union? You only need to be in one. So it's possible that this is an uncountable family of open sets and X is in exactly one of them. Could be in 50, but I'm just going to grab one that I know contains X. Then there exists some, let's say, some lambda naught from our family so that X is in that set. Okay, so this is just one member of this collection of open sets. This is an open set in its own right. X belongs to this open set, which means that there's an epsilon neighborhood around X which stays inside of this open set, and therefore it will be part of the union. That's the rest of the proof out loud. Let's write it down in detail. Since this is open, there exists an epsilon greater than 0, so that the ball around X of that radius epsilon is contained in this open set. But every element in this set is contained in this union. So this open neighborhood is contained in this union, which means that we found an epsilon neighborhood around X contained in the union. Therefore, this epsilon neighborhood is a subset of the union, which I probably could have just continued this kind of subset chain here if you want to write this a little bit more concisely. But let's conclude now that this is open. All right, that's it. Proof is just a direct proof. It's very easy to belong to a union. You just have to belong to one of them. So it didn't matter how many others there were, right? Any kind of union of open sets is open. And the proof is pretty straightforward. It's going to be a little bit different now when we look at intersections. For the third part of our theorem, we want to prove that any finite intersection of open sets is open. We have to consider that the intersection will be empty, in which case it's open. We've already shown that. So let's just do that out loud. If the intersection is empty, we're done. Otherwise, suppose X belongs to the intersection. So I left up most of the writing in the first sentence from our previous proof just to show that the first step was the same. We want to show that for this X, we can design an epsilon neighborhood around it, which will stay inside of this intersection to verify that this intersection is open. Okay, it's very different to belong to an intersection compared with a union. I'm essentially going to rewrite what it means to say X is in this intersection for each of these indices, K, going from 1 through capital N. X belongs to the corresponding set. That's right, this should be A sub K. Okay, so for each of these indices, X belongs to A sub K. And also A sub K is open. Maybe I'll just make that remark too. Okay, so just restating, but I really want to highlight what's going on. Since A sub K is open, we can say that thus there exists an epsilon sub K. So thus there exists epsilon sub K greater than 0, such that the epsilon neighborhood around X of radius epsilon sub K stays inside of that particular set. So this is like an epsilon neighborhood that we are designing for each of these sets one at a time. So we'll have capital N of them. Okay, all of these radii could be different for each of the indices in our family. What's the best thing that we can do with them? So I'll give you a moment to think about that. What we need is an epsilon that will work for the intersection, which means this epsilon has to work for every single one of these sets individually. That means we need to aim smaller rather than larger. So if I have all different types of epsilons, I want to look to the smallest. Let's now let epsilon be the smallest. I'll say the min of the set of epsilons that we picked one at a time for each member of this finite collection of open sets. This is a finite set of positive numbers, so its minimum is one of the elements in that set, so it's positive. Maybe that's worth pointing out though. So then epsilon is positive, and for each k, the epsilon neighborhood around x is contained inside of the epsilon k neighborhood around x, which is contained inside of ak. So this neighborhood, which has nothing to do with k, is contained inside of each ak. So it's contained in their intersection, and at this point, we're basically done. Thus, as desired. And then for trying to learn not to write quite so uphill. Let's see. Okay, probably just as uphill. If the intersection, let's make a note here. The intersection is empty, done. All right, that was what we did out loud. Let me give you a moment to reread this proof, and I want you to ask yourself, where specifically, at what moment, does this proof break down if, like in the second statement, I tried to consider an arbitrary intersection of open sets? So imagine I had any kind of intersection of open sets. There's a spot in the proof that fails. So where's that? And then what I think it would be fun to do is break the statement by considering a few different collections of open families where the collection is infinite, and we'll see what their intersections look like and realize that their intersection might not necessarily be open. Okay, so I'll step aside and then I'll come back, point that moment out, and we will wrap up with some examples. All right, here's where the proof would fail if we were looking at an infinite family of open sets, because if we had an infinite family of open sets and we have one epsilon per member of that family, we would have an infinite collection of epsilons. So there might not be a set minimum like there was here. Instead, we might have to take an infimum, and maybe the infimum of the set of epsilons would be 0. So we wouldn't have a positive radius that we could draw around our point. We wouldn't be able to show the intersection was open. In fact, it wouldn't be. So I think it would be fun now to look at some examples of that. Try to come up with at least one on your own. If you can come up with one, try to come up with another, and I'll give you a few. Coming up with counterexamples is a useful skill to have in real analysis. It allows you to test conjectures. So I could make the conjecture any kind of intersection of open sets is open. So if you have an infinite family of open sets, their intersection is open. I would want you to test this and ultimately conclude that this is not a good theorem. It's not going to work out. So here are some counterexamples that I would like to think of. One useful component to a counterexample when you're dealing with sets is the term 1 over n, because 1 over n kind of allows you to go to, say, 0 in a very controlled way. So family number 1, consider the open sets that look like -1 over n to 1 over n, like that. Each one is just a nice open interval, symmetric about the origin on the real number line. So this is a subset of R. What does their intersection look like? It's not going to have any negative numbers, because if I pick negative 0.02, eventually -1 over n is going to cut that out. It's going to get closer and closer and closer to 0. So we have no negative numbers. Likewise, we have no positive numbers. That might be the easier side to see. That's called the Archimedean principle. So again, if I pick 0.007, if I let n get larger and larger, eventually I'm going to cut that out. So no negative numbers, no positive numbers. On the other hand, the number 0 belongs to every single element in each set. I think I said that wrong. 0 is an element of each of these sets. So this intersection is the singleton 0, which is not an open subset of R. So we're done. Okay, so this is not open. Let's do something similar, just design a slightly different looking family, slightly different intersection. Consider the family B sub n, which is going to be 0 to 1 plus 1 over n. Just want to show you how having this kind of fudge factor in your counterexamples can create things that you want to see. What is this intersection? Same thought process. The left side is going to be 0. Everything between 0 and 1, strictly between 0 and 1, belongs to each Bn. So we're certainly going to have that, but nothing beyond 1 because of this little fudge factor, which drives us closer and closer to 1 from the right. So nothing greater than 1 is in this intersection. However, 1 is in each intersection. So we have this kind of interval. Okay, so those are two counterexamples. Let's do something a little different. How about a sub r equals the real number line, take away the number r. So it's like, here's r. It's my picture's not very good, but I'm trying to just remove the number r from the number line. This is an open set. What does the intersection look like if I intersect over all rational numbers? So consider this set for each rational number. What does the intersection look like? It's irrational numbers. That's not open. You could also do the same thing where you take the intersection for all r in the set of irrationals, you would get rational, same conclusion, not open. I think I'm going to do one more, combining this idea with this notion that 1 over n is a really good piece to work with when you're building up a counterexample. Probably write a little bit more detail for it. So let's call C sub n the set which is real numbers. Take away the number of the form 1 over n, where n is a natural number. Just like before, it's a punctured number line, so I've just removed one single number, so it's open. Let's now prove, though, that the union is not open. If you sketch this, it might be easier to try to sketch Cn by picturing what is not in Cn. Okay, C1 does not have the number 1. That got removed, so this is not in Cn. C2 did not have the number 1/2. This got removed. C3 lost us 1/3, then 1/4, and they start to get closer and closer together. This diagram is not going to be beautiful because now I'm going to start drawing the intersection. So what do they all have in common? Well, all C sub n have every number greater than 1. So that's like, oops, sorry, that was supposed to be right next to 1. This nice open looking piece. All of them have the numbers between 1/2 and 1. So to that nice open piece, we add this open interval, or rather we take the union. We know any kind of union of open sets is open, so it still looks open. Here we pick up another open interval. If this was what the intersection looked like, it would be open because it would be a union of open sets. But something is breaking down here, and that is 0. 0 belongs to each r sub n because 0 is not one of these numbers. It never gets removed. Okay, so to write this like a formal exercise, notice, I'm gonna keep my work somewhat spaced out. Notice 0 belongs to the intersection of all of these Cn. Consider any epsilon greater than 0. Okay, I used little n and capital N. In my picture, and again, just adding to this diagram, imagine I take an epsilon that defines this epsilon neighborhood right here around 0. Notice it's scooped up in the picture, at least, elements which do not belong to the intersection because they do not belong to one of these sets one at a time. That idea is the Archimedean principle, right? So by the Archimedean principle, I'm just going to call it AP, there exists a natural number capital N satisfying that 1 over capital N is smaller than epsilon, which means it's in the epsilon neighborhood around 0. I'm just going to write implies. Oh, that's terrible, implies. But this number does not belong to C sub capital N. I can fit this here. So since it's an element from this epsilon neighborhood is not in one of these sets, the neighborhood itself cannot be entirely contained inside of the intersection of all of them because it contains at least one point that doesn't belong to the intersection. So this is not a subset of the intersection. And I'm running out of room, but I think at this point we've got it. Okay. So again, I wanted to bring up this last final example because this 1 over n construction can be really useful. And here I used it to kind of zoom in. Here we zoomed in on 0, which wasn't open. Here I kind of zoomed in on 1 from the right. Here I wanted to show you like this neat idea that the set 1 over n, which I like to call the Archimedean set, actually, we look at the complement, we pick up 0 as like a sort of strange point. We get arbitrarily close to it with our set, but 0 itself is not one of these numbers, so 0 is in the intersection that we've created here. Okay, so think about this a little bit more. Otherwise, I'm ready to wrap up this lesson. Thank you for your attention.